Okay, now we want to show the state space representation for mechanical system, vibration systems. We know that for this 2 degree of freedom system, we have these equations like m1 x1 double dot plus dx1 dot plus k x1 minus x2 equal to external force nothing, and we have m2 x double dot 2 plus k x2 minus x1 is equal to the external force F. These are the ODEs in the time domain. Clear? Okay. The methodology for these systems is that we have to choose the state variables, let's say z vector, as displacements x1, x2, and velocities x dot 1, x dot 2, and write z dot vector, which is x dot 1, x dot 2, x double dot 1, x double dot 2, and I can write each of these equations like x double dot x dot 1 x dot 1 is z3, x dot 2 is z4, x double dot 1 comes from the equation, so x double dot 1 is minus 1 over m1 d x dot 1, which is z1, plus k x1 minus x2, which is, sorry, x double x dot 1 is z3, k x1 minus x2 is z1 minus z2, and the fourth equation x double dot 2 comes from the equation. This is 1 over minus 1 over m 2, you can say plus f minus x double dot minus k x2 minus x1, so this is like x2, which is z2 minus z1. So this guy can be written as z dot is equal to sum z, so 0, 0, 1, 0, 0, 0, 0, 1. Then we have z1 is minus k over m1. Then z2 is like k over m1. z3 is d over m1. We don't have z4. In the fourth equation, z1 is like k over m2. z2 is minus k over m2. z3 nothing, z4 nothing, plus 0, 0, 0, 1, f. So this equation is like z dot equal to az plus bu. This is the first part of the state space representation. Let's say that output is x2. Let's assume. So y as output is x2, which in our z is the z2. x2 is z2. So I can write it as 0, 1, 0, 0 multiplied by z vector plus 0 as the input. So these two guys, 1 and 2, are showing us the state space representation. Clear? Now, based on this, what we have learned here is that our representation in frequency domain, or time domain, we are showing them by transfer function as function of s in the Laplace domain, or we are showing them by SS, which is state space representation, SS rep, let's say. What are we showing? We are showing the governing equations of the system. So generally, the governing equations of the system for controlled variable is nth differentiation of the controlled variable with respect to time, let's say plus a n minus 1, differentiation of n minus 1 with respect to time, plus we come to a0 c as function of time is equal to b0, let's say r as function of time, r is the input. So I know that this governing equation can be represented as transfer function. How do we show this transfer function? We show the transfer function as output to input, which is b0 divided by Sn plus an minus 1, Sn minus 1 until a0. So if I have transfer function, I can do this changing to the ODE or from ODE to transfer function and vice versa. Okay. If I want to show this as a state space representation, the methodology is like this. I have to choose my x state variables from the first, the zeros, like differentiation, to x2 as c dot of t, x3 as c double dot of t, until xn, which is differentiation of n minus 1c to with respect to time. Okay. In this case, x dot 1 is c dot, which is x2. X dot 2 is c double dot, which is x3. X dot 3 will be x4. And we will go until x dot n, which will be differentiation nth of the c with respect to time, which comes from the equation, the first equation. So how do I write this in the form of x dot equal to ax plus bu? I have to write it like this. X dot equal to x. So the first equation is like 0, 1, 0, 0. The second equation is like 0, 0, 1, 0. The third equation is like, we have the like, okay, and we continue until we come to this last equation, which is x dot of n. This comes from equation. How do we write it? We can write it like minus a n minus 1 minus a n minus 2 minus n minus 3 until we go to minus a0 plus, what do we have as input? We have it like 0, 0, 0, and go until we have b0 here. So you can see that we have some standard form of I matrix, identity matrix here, zeros here, and this guy is from left, from here, right to left, are the coefficients of the equation that are negative, minus a0. So starting from here, going to here, are the coefficients of the governing equation when this guy is 1. We have to make sure that the highest differentiation of the equation coefficient is 1. Clear? Okay. Now, if this equation is somehow more complicated, let's see how. So this equation is like the transfer function of the system is b0 over Sn plus an minus 1 Sn minus 1 until a0. But transfer functions are not always like this. We may have it like this, b0 plus b1s plus until bm sm. So if we have such s's in the equations, I want to show it for the simple case here. Let's say I have b2s2, just two equations. What happens? The governing equation would be plus b1r dot t plus b2r double dot t. So the changing between these two guys is clear for us, and the transfer function or the ODE of the system can be represented easily. What we do here is that we separate the equations as cascade. It is like I have the input R, so the transfer function, the first part is the one that we had, let's say 1 over Sn plus an minus 1 Sn minus 1 plus a0, give me some parameter x1, and then it's cascaded by, multiplied by b0 plus b1 s plus b2 s2, gives me the c as controlled variable. This is possible, yeah, to write the total transfer function as some two multiplications. So in this case, what do? We say for this part, I have this equation already. Let me copy, paste it here. Let's also name this as not x1 but z1 so that x's are not mixed up. Okay. So what do we do here? First of all, this guy should be 1. The edits are like this. This guy should be 1 because b0 here changed to 1. So this guy should be 1. Then we say that this equation, let me come here. If I had the output here, what was the output here? It is C. So it is like C is the first variable. This is the output equation that already we had. Now our output equation would be changed. So this changed to y, and output equation is c, but this time it is multiplied by x. How? The first we have b0, then we have b1, then we have b2. How we do that? It's like this. C is b0 z1 plus b1 sz1 plus b2 s2 z1. b0 z1 is b0 x1 plus b1 sz1 is z dot, so it's x2, b1 x2 plus b2 x3, because x1, we know that x1 is c, x2 is c dot, x3 is c double dot. It's like these are differentiations, so I chose instead of x sum z, so their differentiation is contributing to the c, the zero differentiation, first differentiation, and second differentiation. So what changed from the previous problem to this is changing this guy to 1 and writing the output equation in appropriate form. Any question? No question. If we want to do vice versa and convert from state space to transfer function, I know that in state space I have x dot of t is equal to a x of t plus b u of t, and y t is c x of t plus d u of t. So if I Laplace transform these guys, I will have sx of s equal to a x of s plus b u of s, and y of s would be c x of s plus d u of s. So from the first equation, I can say S identity minus A matrix xs is equal to b us. So from here, xs is S identity minus A inverse multiplied by bus matrix. So I can say y of s is c multiplied by si minus a minus 1 bus plus du. So the transfer function is output to input, and it can be written as c si minus a minus 1b plus d. So this is conversion from state space to a transfer function representation. Any question? No question? Okay. Now we want to have several examples in order to understand what we have already explained in this lecture. It says that convert the following transfer function into state space and draw the block diagram of the system. What we learned here is that this guy has governing equation like this: c triple dot plus 9 c double dot plus 26 c dot plus 24 c is equal to 24 r time. This is the conversion from ODE of the system, if we consider one ODE for the whole system, and the transfer function. And we learned that for this system, x1 is c, x2 is c dot, and x3 is c double dot. So x dot 1 is c dot, so it is x2. X double dot, x dot 2 is c double dot, which is x3, and x3 dot, which is c triple dot, which is 24r minus 24c minus 26c dot minus 9c double dot. It can be written as 24r minus 24c, which is x1, minus 26c dot, which is 26 x2 minus 9c double dot, which is minus 9 x3. So I can say that also this guy is like 0, 1, 0, 0, 0, 1. This is the I part, as I said, identity part. And the last part is like minus 9, minus 26, minus 24. So starting from here to here, we put it here, plus 0, 0, 24 r of t. And what is output? Output is c controlled variable, which is the first equation, 1, 0, 0. That is multiplied by x. So this is called phase variable representation because we are choosing these variables. Now I want to draw the add page, and I want to draw the block diagram. Let's see how we can draw the block diagram of this system. Let me copy this, paste it here. Okay. In order to draw this block diagram, I have to do this. I have to say the input is RT, the output is C of t. What do we have as other signals? I have X1, like X1. I have X2, and I have X3. So these are the names. So then I have X dot 1, X dot 2, and X dot 3. So from here, I need some integration to get to from X dot to X. The same thing I need here and here to do the differentiations from X dot. Now let's say what is X dot 1? From equations, X dot 1 is X2, X dot 2 is X3, and X dot 3 is minus 24 X1 minus 26 X2 minus 9 X3. So I have these three equations. It means that the first equation, X dot 1 is X2. So I need this guy to be equal to each other. So I just connect them to each other. Or second equation is X dot 2 is X3. So X dot 3 is X dot 2 is X3. So I need this guy. And the final equation is like X dot 3 here is minus 24 X1. So I need minus 24 X1 minus 26 X2. So from X2 minus 26. And from X3, I need minus 9. And also we have plus 24R. So I need this like 24 from here. So this is the We can say these are plus and these points are negative here. This is representing the, and output C is like YSC is 1, 0, 0, X. So this means that C is X1. So this is C is X1. So connected like this. This is the representations, like we had an ODE, we could show it by status space representation, we could show it by transfer function representation, and each of these can be converted to each other. Now, if I have this example, which is much more complicated, so the idea is like this. X dot would be, I need three x's, like x1, x2, x3. I need 0, 1, 0, 0, 0, 1. This is phase variable representation. Then I will need minus 24, minus 26, minus 9, x plus 0, 0, 1 multiplied by RT, and y is equal to 1, 1, 7, sorry, 2, 7, 1, x would be the output. So how do we write this? It's like the output y is S2 plus 7s plus 2 multiplied by x, which is, we have 2x1 plus 7sx1 plus s2x1. This is 2x1. This is 2x dot 1, which is x2. And this is x double dot 1, which is x3. So, okay. Now I want to show the block diagram, or I can show the signal flow graph. I say the signal C is here. Signal X1 is here. Then we have signal X2, signal X3, and R. So I need X dot also. Here we have integration 1 over S. Here we have integration 1 over S. And if this is X dot 3, here we have integration 1 over S. Now, what do we have? The first equation says x dot 1 is x2. So x dot 1 is x2. This means x dot 1 and x2 are connected. The second equation is x dot 2 is equal to x3. So x dot 2 is x3. That's done. And the third equation is x dot 3 is minus 24 x1 minus 26 x2 minus 9 x3 plus r. So minus 24 x1 for x dot 3. So minus 24. Then minus 26 x2 minus 9 x3 and plus r. What about the output? Output y is 2x1 plus 7x2 plus x3. So 2 from x1, 7 from x2, and 1 from x3. This is the signal flow graph of this representation. Clear? So phase variable representation For system, we discussed like this. 24 comes here, from here. This guys get here negative. And if we have like from like S2 like plus AS2 plus BS, something like this, then this guy to change 1, and these become like 24B and A instead of 100. This is the gist of what we discussed for phase variable representation. And this is like C, this is like C dot, this is like C double dot of the system. Any question? No question? Okay, let's have a break, guys.